Hello, everyone. Hello,
Hello,
friend.
how are
Welcome.
you?
I'm good. I'm good. It's a little bit dark outside here in Florida today. We have some nasty storm approaching us, but it should
Oh,
hit us in a few hours. So hopefully I will not lose connection, but if I will lose, you will be able to continue this this stream. How
yeah,
about you?
no, no
You're
problem.
kind of
I don't have
your
this problem here.
yep. How are you? Like your background doesn't look usual. Usually you connect from a different
Yeah,
location.
I'm from a different place. That I blurred the messy background. Yeah.
Nice. And hello to all of you, my friends. Thanks for joining us live today. I see that many of you are joining us on LinkedIn, on YouTube, on Twitter, on Instagram. Thanks for coming. Thanks for coming. Today, we are going to explore the internals of Postgres and YugabyteDB in action again. And what we usually mean in action is we try our best to skip all the slides, and our approach is to have terminal sessions, a few browser tabs, and just to show you with hands how things work in practice. Because then, if you decide to read or learn more, you will be find some wonderful content on the internet. Today, it's all about action. Just so that let's tell us where you are joining from, what you would like to learn from this session, and what's important. We always have some predefined, pre-selected topic for every live stream, but this live stream is called community open hours, which means that feel free to interrupt us and ask the questions that are interesting to you, whether like when it comes to YugabyteDB or to Postgres, and we will do our best to answer them during this stream.
Yeah, on the chat on LinkedIn, YouTube, Twitch also. I don't think on Twitter there is a chat, but yeah.
Not yeah. Actually, we need to explore how can we when we stream to Twitter, it's usually streams a post in Twitter, not let's say that streaming icon or cloud that you see at the top of X of Twitter. Probably at some time we need to explore how can we do this with our streaming platform, but looks like it's not possible yet. Uh, so let's get to the news, Frank. So what are the news? What are the most interesting things that happened in the world of YugabyteDB
So
throughout the
let
last?
me share something special for our users in Asia. We have a distributed SQL Summit (DSS) conference, virtual conference that we do one time a year. We have a global one and we have a special one in Asia. Of course, the content is accessible from everywhere, but the time zones are more Japan or India or Singapore friendly. And do we have so yeah, first the link is distributedsql.org, and there if you go to agenda you have the one in Asia, and there are some talks. I'm doing one. So here are our speakers, people from Yugabyte or customers or others, and yeah, we have the agenda there, and you can
What are you talking about? You're
attend
talking
from anywhere. And yeah, I was just looking. There are some talks in Japanese, of course, because the team there is doing some talks or with customers also. And yeah, mine is about comparing. Yugabyte with Postgres and the vehicle for just some technical components. The things that are really different, LSM trees versus bit trees, MVCC, the kind of thing that we are also doing in these open hours. But just to put some facts
yeah, this
behind that.
sound like yeah, something you I do believe that you covered this extensively across several in the series of your articles. But
Yeah.
this video content is good.
And those are questions that we have from people who migrate. They know that we are Postgres compatible. So from the application point of view, it looks like Postgres, but when you go deep into the storage, it's of course different because it is distributed.
Like it. So folks, if you live in Southeast Asia, like in APAC in general, this DSS summit is friendly for your time zone. Take this opportunity to join and not just to watch, but also to have a conversation. We truly have a brilliant team based of that region, and we had some offices in India, we have offices in Japan, etc. And we keep growing. So join it, ask questions. If you live in other places like Frank or I, like in Europe or the United States or any other countries of the world, you're also welcome to join if you just probably, but it might be way too early or way too late for you, but you will be able to watch that on demand.
Yeah.
Do me a favor, my friend, share this link with everyone here
Yeah, sure.
and on LinkedIn. And in the meantime, I will share with you folks another quick piece of news, and then we will get to the main topic, to the internals of memory in Postgres and YugabyteDB. What I wanted to share, I'm less prepared than Frank when it comes to this screen sharing. That's why it takes me more relations to find this present button. One day I will nail it. One day I will nail it. But this one. So those of you who join our community live streams regularly, you know that a few weeks ago we did an episode on the PostgreSQL and YugabyteDB internals in relation to MVCC, to multi-version concurrency control. And eventually, Frank and I, we were invited by Alex Petrov, the author of this book. And probably all of you who are on this stream, I guess, at least either read or heard about the book. This is a brilliant book that was created by Alex a long time ago. And Alex invited me and Frank to meet with his community in the Discord channel to discuss the internals on VCC in Postgres and YugabyteDB. So if you missed that episode, make sure to join us. It's gonna happen when? It's gonna happen next week. It's happening on, I think, let me check the calendar. April 8th, right? It's gonna be April 8th.
I think it's next week about the same time as now.
Yeah, it's April 10th. It's gonna be at 11 a.m. Eastern time for those who live in the United States, and which is like 5 p.m. or 4 p.m. in Europe, right, Frank?
Yeah. 5 p.m. for me. So yeah, the same as our community open hours that are every 2 weeks, and then next week is free for us.
Yeah, wonderful. I saw that you have already shared this link.
Yeah.
You know what? For some reason, when I go to LinkedIn, I don't see any comments. Have you shared this on LinkedIn or not yet?
Oh no, I forgot that we have to share it on LinkedIn.
Yeah.
Let me do it. Yeah.
All right, let's do it. So, folks, what you can do if you want to get connected with this community, you can join this Discord channel, and you can just join our session on MVCC internals in Postgres and YugabyteDB. And also, Alex tries to put together a regular cadence of different interesting, events around the database internals. So, like, probably that's going to be a wonderful introduction for you, and then you will be able to come to his community. Go, join, and hopefully we'll see some of you next Wednesday around the same time. Now, I don't need to stop screen sharing. Let me quickly check the questions. Do we have any questions? Oh yeah, we've got a hello message from Yogi. Yeah, Yogi actually is colleague of us. This is one of the most, experienced folks at YugabyteDB who knows exactly how to use YugabyteDB at different scale. And exceptionally, folks, if you live in that territory in APAC and you will have a chance to work with Yogi on your project that uses YugabyteDB, it's going to be a wonderful experience. Just believe me. Thanks, Yogi, for joining, and thanks for saying hi to all of us. All right, so let's get to the main topic. And folks, as always, feel free to interrupt us. You will not be able to interrupt us, right? Because you cannot talk. You cannot talk during this live stream, but share your questions, and at least every 5-10 minutes we will be taking polls, and we will be checking like if there are any questions across different channels. Now, the main topic: internals of memory in Postgres and YugabyteDB. And why do we do these databases together? We will not be able to cover all the internals because 1 hour is obviously not enough. That's why today, when it comes to Postgres, I will be primarily focused on the Postgres shared buffers memory, and you will see how those shared buffers are used in action. Some basic and a little bit deep information. And then Frank will switch to YugabyteDB. And why do we usually cover those two databases? Because YugabyteDB is built on Postgres. The query layer of YugabyteDB is exactly Postgres. And we want to have this series of internals during our community open hours just to show you how those two databases are similar or different when it comes to different areas of their architecture.
When you start to look at performance, for example, you will see some difference because of course the implementation is different. There is no difference from the API, from the application point of view, but looking at performance, of course, you need to know how memory works and is allocated.
Let's start.
Yeah.
Okay, which means that I by mistake stopped sharing my screen, and now I'm trying to find. Let's where is this button? All right. It's confusing. The interface, the user experience sometimes is confusing. All right, so I will start with few pictures. As I said, we don't use slides, but here as I understand that not everyone knows the details, I want to start with the following situation. Let's say that we have several users, clients, and they are eager to connect to Postgres. They are probably using some of your applications, so they just want to connect to the database and do some stuff. And they're not connected yet. And here is we have two other folks who have already connected to Postgres, and we have client session number 1 and client session number 2. So when it comes to the Postgres architecture internals, and we are not talking about the memory yet, those who are going to connect to the Postgres, they will be connecting to the Postgres post master process. So this is the process that listens for incoming connections. So whenever you're connecting from PSQL, from your application, etc., you always connect to this post master process. If we take these two guys, client 1 and client 2, what happened? They also were in this crowd before, but once they connected to Postmaster, the Postmaster process forked instances of Postgres backends for every client session. So this is how Postgres functions. If you don't know, Postgres is not multi-threaded database. It's a database that uses multi-processes approach. Basically, there is a process for every client session, for every client connection. And so this Postgres Postmaster basically forked these two processes. So we have this Postgres backend that handles the request for the client number 1, and we have Postgres backend that handles requests for the client number 2. Obviously, those backends, they use memory, RAM, DRAM that is available on your machine, on your server or your container. And this is not exhaustive list. For instance, you will have so-called work memory that will be used by those backends if, let's say, when they execute some types of queries. For instance, you execute query and you need to order the result of that query, or you need to do the hash join of between several tables. The work memory is going to be used. So, and this work memory is created for several, like it can be every query will have its own work memory during its lifetime. Also, you can have this temp buffers, temporary buffers, and these buffers are used if you create temporary tables for this client session. They're not shared across sessions, that's why they're just stored in memory. And there will be some other private memory areas that are used by these Postgres backends exclusively. So these areas like work mem is not shared between those processes. But what happens from the memory standpoint as well, when you start the Postmaster, when you start the database server of Postgres, the Postmaster will also create the shared memory on your machine. And this shared memory region, let's call it like shared memory region, will be shared across all of the Postgres processes that need to get access to it. For instance, this Postgres backend and this Postgres backend 2 and Postgres backend number 1, they will be able to see all the data that is stored here, and they will be able to update the data in certain areas of this shared memory. So this shared memory is not, just one continuous chunk of memory that is used for all the different needs. In this shared memory, within this shared memory, you have several segments that are used for different purposes, or several areas. For instance, you have shared buffers, cache, and this is the main topic of our conversation today. I will show you how those shared buffers are used in practice. But then we have wild buffers, write-ahead log buffers. So whenever your application does any changes, the changes are first written to these buffers and then they are synchronized to disk. And this arrow means that sometimes those changes can go to the operating system cache first and then they will get to disk. Sometimes they can bypass the operating system cache and go to disk directly. It depends on your configuration. It's configurable in Postgres server. And then you will have other types of memory that is stored in the shared area. For instance, you have the memory for logs. When you have these two sessions, and those two sessions, for instance, trying to access the same data at the same time, you have transactions, you will be using different logs, and those logs are also stored in the shared memory. They are visible to all of the processes. So this list is not exhaustive. There are many more areas that we don't want to discuss today. But our primary guide for the today's conversation is these shared buffers. So this is the most probably interesting from the application standpoint. When you have your application, and let's say your application tries to read some data from a table or put new data in the table, this read or write always goes to the shared buffers first. And these shared buffers are here, they're visible to everyone. If let's say you're trying to read a record, then Postgres will try to find this record in the shared buffer. If there is no any buffer for this record here, it will go to the operating system cache. If it's not in the operating system cache, it will try to read it from disk. So this is the flow. It always goes to the shared buffers, then to the operating system cache, and to the data files. This is for the reads. The writes are not that different. The writes also go to this shared buffers cache, but then they're not written to their data files immediately, because that would kill your performance, right? Usually there is another process that is not shown here. It's called write, like I don't remember the name, like by basically like something like checkpoint or background writer that starts and writes all the dirty pages from the shared buffers to disk. Okay, so this is what happens in Postgres. So this is the high level architecture.
Can
Hopefully
I
it
add
makes sense.
something?
Sure.
Because usually we see the shared buffer as the main purpose being a cache to avoid disk I/O. For me, the main purpose is to be shared between the processes, because when you have multiple sessions reading and writing, they cannot read and write directly to file. Even if it's not a problem with performance, it's a problem with consistency. You need a single point where you have a buffer and all sessions can go. And this is why it is shared between multiple processes. The first goal is to share the data so that reads and writes will all work on the same version, and then using it as a cache to asynchronously write to the disk.
Exactly, exactly. And why, and again, if to highlight you, like why Postgres uses this shared memory. And this shared memory is a basic feature of Linux and other operating system. You can create your two applications, right? Two application instances that run on the same server, and you can get them working together and accessing the same shared memory. It's visible. But Postgres is multi-process system, meaning that you have these two standalone processes that handle two different client sessions. And they certainly might be dealing and updating or querying the same data. They have to collaborate with each other, right? And how can you ensure that two processes of Linux or Windows can collaborate through each other? They can collaborate through this shared memory segment. Other databases that are multi-threaded, like MySQL, and I guess that Oracle is also multi-threaded, they don't need shared memory because they start as a single process and they have the common memory and they can interact with each other. But Postgres is different. We're not going to discuss what architecture is better or worse, but this architecture works exceptionally well for Postgres, which means that it's totally fine. Questions. Let's quickly see. Before I go now, I want to go to my terminal and show you some of the examples, but let me see if you have any questions.
First, we have Fatih, who just asked us to compare the features with Oracle as we are talking about them. And I think Oracle is closer to Postgres than to Yugabyte because it also uses shared buffers, which is the buffer pool. It's very similar in the sense where you have those buffers that are protected by the redo log that are the wall. The main difference is that Oracle can write directly to disk bypassing the OS cache. So with Oracle, you can use the OS cache, but you don't need to. And usually it's better to save memory, allocate the memory to the shared buffer pool, rather than the OS cache. So that's the big difference with Oracle. You don't have this OS cache in between, this double buffering.
And friend, question to you now. I'm curious. Like that shared buffer cache in Oracle, is it the same like shared memory, or is it just part of that single Oracle process? Because Oracle is
It
multi-threaded,
is shared memory
also
using,
shared
of course,
memory.
it depends on the platform. On Linux, it is using the shared memory segments of Linux. In in Windows, it's a bit different because in Windows, Oracle works as a single process and threads, and then they can share the memory without any other structure. But it's the same idea, yeah.
Oh, cool, cool. And actually, this what you said, like in Oracle, you basically in Postgres in production, actually, you don't have this option for bypassing this operating system cache between the shared buffers and the disk.
If you do that, the performance will be very bad. Mostly, there are many reasons, but one reason is that Postgres always reads and writes single pages. So if you do a sequential scan and you read contiguous pages, contiguous blocks, Postgres will do many IO calls and then relies on the buffering on Linux to do some read ahead to avoid sending those many IO calls to the storage. Oracle has multi-block reads, so doing that, doing larger IO calls.
All right, all right. And also, I asked this question on Twitter yesterday, and the Postgres community folks responded me that you can bypass this operating system cache between the shared buffers and disk. For the development in Postgres 16, they introduced a special flag that allows you to cancel this, but that's a developer flag, meaning that no, you are extremely discouraged from using it in production, which means that in production, you can bypass this operating system cache between the write-ahead log in shared memory and on disk, but shared buffers and disk, no, usually you need to use this one. You have to use
It's
this one.
work in progress, so there are already some parts of it in the latest version of Postgres, but it will take a few versions to get it fully working without the OS cache. Yeah.
All right, let's get to the let's get to a few examples.
Yeah.
All right, so this is what I've got: an empty terminal window, and I think I have Postgres running in Docker. Yeah, it's Postgres. Yeah, with PLVL extension. I'm preparing for one of my sessions, but this is I think one of the latest versions of Postgres. Let me connect to that version. My password is hard to guess. It's just password. That's their 16. Yeah, the latest version of Postgres. I guess that I prepared, and which means that I cleaned this database. It's empty right now, and today I want to start with my favorite example. Let me do the full screens. Increase the font size a little bit. I want to create the account table. It's gonna have the ID of the integer type and the balance of the money type. So let's say we are thinking about the people who have some bank accounts and they have some money there. Now I want to use one of my favorite features of Postgres, this generate series function, to insert some dummy data into my table. What I'm going to do, I'm going to generate 100 accounts using the function, and then I will use these IDs as an ID for my account table, and then for every ID, I will generate some random balance number, like of the money type. So once it's generated, let's take a look at one of them. I'm selecting from account where ID is equal to 5, and that's the balance and that's the value. So now the question is, we are talking about the shared buffer cache, and my question is, where did I get this record from? Did I read it from shared buffers, or from operating system cache, or from disk? In Postgres, it's very easy to discover. We have this wonderful feature called explain statement, and there you can pass analyze and buffers parameter. Many people in the Postgres community suggest you to use buffers at all times. When you execute it, what you will see, we are doing the sequential scan. Even if we try to get the single record, we are doing the sequential scan. Why? Because I don't have any index yet. I just created the table. There is no any index. And from the buffer standpoint, that was the plan. It said that I would need to read 8 buffers, but in fact, I read only 1 buffer, and then it read all of the records, and all the remaining records were filtered out, removed, and it returned me the record with the following ID. So what happens if we continue this exercise? Let's say that I want to get all their stuff with the ID bigger than 50. this one has not changed. It's the same sequential scan. The filter condition has changed, but we are still, from the memory standpoint, we are reading this from shared head. Shared head means that we found this record in the shared buffer, folks, and that shared buffer that is shared with all the Postgres processes. And we had to read just one buffer. So the question is, does it mean that all those records are located in one buffer? Because what I'm looking at here, like it said that Postgres for some reason think that it would need to read many more buffers.
Let me correct that. The buffers that you see under planning are the buffers that are read for planning, read from the catalog.
Okay.
It's not the estimation. For example, if you run it again, you will not see the planning. You will not see the.
Wonderful.
You will see the planning phase, but you will not see those buffers. No.
Cool. This is why we are doing this together. Now, but generally speaking, if we do just this dummy request, not this obvious request, I want to read all those 100 accounts that I have. Still, sequential scan, and we are reading just one buffer. So it feels like, if to judge by this explain, analyze all the data that I generated, and this is a very tiny database, the data fit into one buffer. Okay. The question is, what's the size of this buffer? And do I have more buffers associated with this table? We can easily check. Postgres has a very, how do we check? Postgres has a very broad ecosystem of extensions. And there is obviously an extension that allows you to look into to get insights or look into the internals of the buffers, of the shared buffers that are used by the database. The name of the extension, and we are going to enable it right now, create extension command, pg buffer cache. So it's easy to remember. And it comes prepackaged with your database. You don't need to install it separately. Once you do this, you can make the following call to the pg buffer cache summary function, and you will get this. So what do we have in the database, in the entire database? You remember when I was telling you that when, where is it? When Postgres starts, the Postgres postmaster starts, it will allocate this buffer. It will allocate the shared memory. And in the shared memory right now, we have a lot of buffers. We have 927 buffers that are used by someone. And then we also have more than 50,000 buffers that are not used by anybody. 40 of those buffers are dirty, meaning that they have to be flushed to disk. They are just in memory, they have to be flushed. This buffers pinned is just one of them. Like pinned, it means that there is no any client session that puts a lock on any of these buffers. So this is the basic information. And the question is, who uses these buffers? We can execute, I think, which one? The following function. Yeah. So what this function does, it will make a call to the pg buffer cache view. It will read the name of the relation and the total number of buffers that are used by every relation. But to get those relations, we need to join the buffer cache view with the following relations, pg class. And this one, I don't want to analyze it, but generally what you're getting in return, you're getting this list. You're getting that in the Postgres catalog namespace, we have the following relations, and those relations also use the buffers. So like that shared buffer cache is not used only by your application tables and indexes. They are also used by Postgres internal relations. However, if you want to take a look at a specific relation, like I have this account table, and I want to know exactly how many buffers are associated with this account table right now, I again can make a call to this buffer cache. You can query, specific information that you need right now. You make this call, and what we see, yeah, we have just one buffer. We have one buffer, which means that all the data, you remember we were doing that select from the account table, sequential scan, all the data fits into this buffer. Okay. Is it dirty? No, it's not dirty, which meaning that we have a consistent copy of this data on disk. It was synchronized by Postgres already. This usage count, actually, a metric is very interesting. I don't want to go into details, but 5 is the maximum number. It's like capped by 5. You can Google, but it will never go beyond 5. It basically increased whenever sessions put a lock, whenever the sessions that connect to Postgres, they put some locks on the buffer when they pin it. then this number will be incremented. Then this number can be, like in background decremented. But generally speaking, it's not that important for our today conversation. Just we can probably discuss that sometime in the past, unless you, Frank, have any insights into this and you want to add.
No, just I think it's used to flush the dirty buffers, keep the ones that are frequently used and flush the ones that are not used frequently.
Yeah. From the usage standpoint, that's an important part, because Postgres, that shared buffers memory, it's limited, and sometimes you would need to evict some of the buffers, evict some of the pages, right? Which means that this usage count flag helps Postgres to decide what buffers have to be evicted from memory and what buffers have to remain in the memory. Now, another thing that I wanted to show you. The data set, I have only 100 records, and the data set obviously fit into their one buffer. I can read the following, I can check the shared buffer size. That's the configuration that is stored in Postgres. It's 8 kilobyte. And actually, this 8 kilobyte is equal to the default size of a page in Postgres. It's also 8 kilobyte, and looks like all our data that we generated fits into one page, and that one page is just fits into one shared buffer. That's it. It's just one-to-one mapping right now. Now, what I want to show you is what happens if you decide, let's say, to update any of your records. Let's do this one. So right now you see that this one is this dirty flag is set to false, meaning that all the data is in a consistent state and it's stored on disk. But let's say that I want to update table account, set balance to 600. It's of the money type, where ID is equal to 1. It's updated. And now you can see that this flag is set to true. What does it mean? It means that Postgres certainly synchronized this change to the write-ahead log file. And we have consistent copy on disk, but in the write-ahead log file, because it's much faster operation. But that change was not synchronized to the data files. Instead, it was written to their buffer cache in memory, in the shared memory. And then a little bit in some time, probably sooner enough, it will start the checkpointer, whatever, and the checkpointer process will synchronize this buffer and page back to the disk. So now if I execute this one, yeah, it's still true, but eventually it will be synchronized to disk. The next example, what I wanted to show is not this one. Okay. Let's do this. I want to generate more data. And to generate more data, we can use the same command. Let's say that we generate series. Now I want to add more records from the ID 101 to, let's say, 10,000. We inserted more data. And now if we execute a request like this one, yeah, let's query all the data from the accounts table. You can see that we are still doing this sequential scan. And this time we had to read 55 buffers. So which means that to hold all this data right now in our accounts table, Postgres had to allocate 55 pages, sorry, and those 55 pages were mapped to the 55 buffers. You can always check this easily if you execute the same call to their PG buffer cache, our account table. You will see that, yeah, right now we have many more buffers, okay? So this is how it looks in practice. Interestingly, also, you remember when I want to find a particular record, like account with ID number 10, from account where ID is 10, what happens? Sequential scan, because I don't have any index. And when I do the sequential scan, I have to read all the buffers, all the data, right? But at least the good news right now, we don't need to read them from disk, because all of them are stored in the shared memory. What I want to do now, let me show you that this is in fact the shared memory. It's shared between different Postgres processes, between different Postgres backends and sessions. We are splitting the terminal, and I'm opening another connection to Postgres. I certainly have access to the account table. And if I want to execute exactly the same request right now, you will see the same statistics. I mean, like we are reading this data from the shared buffer cache. It's all shared. You're not reading it from disk. It's available for everyone. Now, for the sake of optimization, what I want to do, let's say that when I'm querying a specific record, I don't want to read all this data, all these pages, right? I don't want to do the sequential scan. And with this, now I want to create a primary index, and I want to demonstrate you that the shared buffer cache in Postgres is used not only for the tables, but it also used for indexes, because many times whenever we run requests over our database, we use indexes. And also it's good to have index pages cached in memory. Let's do this one. We need to alter table account at primary key for the ID column. And also a good practice is to run vacuum analyze so that Postgres can rebuild statistics. Vacuum analyze. It's done. Now, my friends, if I repeat the same request, I'm trying to read the balance for the following record. Let's see what we get. What has changed? Now we are doing the index scan, obviously, because we created the index. And during this index scan, we read one buffer from the shared cache, but the other two were read from the operating system. And this big plan doesn't say us whether we read this from the operating system cache or from disk. There are some other tools in the Postgres that can help you to answer this question. But right now, this flag that says read to means that 2 out of 3 total buffers, pages, were read from the operating system. The good news is this is the shared, right, buffer, and it's shared between different processes. If I run the same request here from my second session, that's my second client, think about another, let's say, microservice connecting to the database. Look at this. Now, we are not reading it from disk or from the operating system cache, because when I executed this request from another session for the first time, Postgres read these 2 pages from the operating system and put it in the shared buffer cache. Now they can be reused. Finally, remember this query where we were trying to get the total number of buffers for our account table? You can do the same for your account primary key. So that's the name of your key. Now we have these 3 buffers, right, that are in memory. Let's change the condition a little bit. What if I want to get for the ID with 1000? Take a look. So two index pages were already in the shared buffer, and another one that was required for this request were not there. It was read from the operating system. Now, if you refresh the statistics, you will see that, yeah, right now we have 4 buffers stored for this index in memory. Let's make this a little bit more complicated. What if we do this range query if you want to do between 1000 and ID is less than 5000? It will be a little bit more aggressive. Yep, index condition 11. Yeah, this one I don't know actually, Frank, why it says that it found 25 buffers in the cache. Probably it was because I had only 4. I see that
It can be multiple times the same buffer, because you read, actually it's the number of buffer pinning. So you read many index entries, and for each one you go to the table and they are scattered into the table. And then maybe for another entry, you will come back to a block that you already have read for another row. And this is where the index scan can be slow. It may read more pages than you have in the table, just because it read them randomly at different places.
Cool. Makes sense. And now if we check the total number of buffers here, you will see that this is what we store for the index. And again, those might not stay in memory forever, because once you start putting some load, right, Postgres will start evicting these buffers depending on the usage count number, right? And you can actually, you can order by usage count to see descending, right? We need to do descending to see, yeah, some of the buffers were used more often. Probably this is the root of the index.
Yeah, root and branches of bit tree hopefully stay in cache here.
But as always, if you now repeat the same request here, all the buffers are in memory. Yeah, and we read them 36 times, right? Cool. So that's it, folks. This is how it looks and works in practice. And this is how it works in Postgres. So in Postgres had the shared memory, and today you saw how it works in action. Postgres will try its best to use this shared buffer, and then if the data is not found in memory, it will certainly go to the operating system cache or disk. And the same happens for writes. The writes that whenever you change your data, whenever you update your indexes, etc., the changes will be accumulated in the buffer cache first, and then they will be synchronized to disk. All right. Let's check the question, and then we would need to switch to Yugabyte. All right. What do we see? Do we have anything in LinkedIn?
I don't see any question, but check yourself because sometimes
I see one question. Yeah, I see a question from Fatih. Let me copy it so that everyone sees it. Linked Fatih.
And while you do that, to transaction with Yugabyte, I will mention that those shared buffers are really, really nice when it stays within one server because it's easy to share memory between processes. When you want to scale out to multiple servers, you cannot really share the memory between multiple servers, especially if they are far. I mean, there are some solution to share the memory when they are really close, but we need something else in that case.
Greatly. So for the question of Fatih, what happens during a race condition for buffer cache and what are the observable side effects? This is actually related to the logs. You see this in this shared memory, like we have, Postgres has various logs. Postgres has this MVCC multi-version concurrency approach control that allows you to see whenever you start your update, your select or your transaction, you will see only what you're allowed to see. And Postgres had that. Every record in Postgres, what I can show you right now, it has an ID associated, like every record has a version. For instance, when I'm querying this one, let's say I want to select from account where ID is equal to 5, you see this data, but also there are some hidden columns, and this is what we discussed in the past, xmin, xmax. Like that's the idea of the transaction that created this version of the record. And Postgres can have, when you execute transactions, for instance, let's say you have two sessions that are trying to update this row, this particular row. Then the transaction that is updating, it will put a lock, and that lock will be stored in the special area of their shared memory. And the transaction that is just trying, like not a transaction, a query that is trying to read, right? It will see only the data that was committed, that was visible. So this is pretty much a very high level overview. So the race
And
condition.
how do you see that? You will see you have wait events in pgstat activity, and then you will see those lightweight logs in pgstat activity. When, for example, in your demo, you had a session that had to read a page from disk, put it in the shared buffer. If at the same time I want to read the same page, I will just wait that you have put it on the shared buffer, used it, and then I will be able to use it. So there are some short waits for on that, and there are some wait events. The equivalent of Oracle buffer busy waits. Same idea. You cannot have when you read a page, you need a share lock to prevent anyone writing it. When you write to it, you need an exclusive lock because nobody can read while you are writing to it.
Yeah, hope it answers your question. So we've got another question from Vibor. Yeah, sorry if I mispronounced your name. So the question is, what weights do you see in Postgres if buffer is pinned in exclusive mode? Let me find something. So I will not be able to demonstrate it. Frank, if you want to start answering, you feel free.
Yeah, but I don't have the name out of my head. It's a lightweight lock, and there are multiple cases. For example, the one where I said where it was reading from disk and you are waiting for the other session to read from disk, I think is transaction buffer. I don't know exactly the name of the wait events.
Yeah, so what also don't remember the name of the wait event, but here is I will share with you, Vibor, this link. It was written by the Postgres professional folks. So they are one of them also contributors to Postgres. So this one, like whenever you see this buffer pin, right, pin stuff, they actually use this one of the logs, like it puts some lock, and what type of lock it is?
I
Yes,
don't see it,
some
but
yes,
there are some buffer mapping when it's about mapping it to the shared memory.
yeah,
There are some buffer
yeah,
content.
yeah, they call it lightweight buffer mapping lock.
Yeah.
I think that yeah, at some time in the future, Frank, and that's a good point. We should cover different types of locks that exist in Postgres and how they're put. But that's a wonderful exercise. So in the meantime, let me folks share this article with you. You can get a little bit more insights from there, and we will think about scheduling a dedicated session on this topic. So sharing this one on LinkedIn, and also I will share on StreamYard. So Frank, let's get to YugabyteDB.
Yeah.
Let's see now, like,
Let
get
me
a little bit of internal.
directly share my screen. So I started a buffer. I started a cluster with the Docker compose that I have, that I call YB Metrics Lab, that we already have seen. So I will not go into the detail. In this Docker compose, I also expose a lot of metrics and display them with Grafana with nice colors. And what I will do directly is I will create a table. So I set use hash splitting to off because I don't want to hash split. I want only one tablet to make it simple. And I will load data in the simplest way, disabling transactional writes just to show the simplest thing before the real thing that is fully ACID. So here I can refresh, select my demo table, and we will look at some memory constructs. We don't have shared buffers on each node because we cannot share them between multiple nodes. So we have also a different structure than B-tree that where it's easier to work on it with high performance without shared buffers, because the battery really does a lot in the blocks, in the root, in the branch, in the leaf blocks, can split them, can update them. This is fast when it is in shared buffer. You cannot do that when the block is on multiple nodes. So basically, I inserted a small amount of data, about 15 megabytes. And if I look at the most important memory component, first, I'm connected to a Postgres backend, which allocates some memory. And this kind of copy put that in memory. And this is why for my session, I see 16 megabytes allocated there that were active when it was running and just staying there in my idle session. So that's one thing. Then this data is sent to the server, to the tablet server, and finally to a tablet where it has to store the data. Here, I see a statistic that is called tablet overhead. The name is really bad. We will detail that, which the main component here is the memory table. So when I insert rows, it goes to a LSM tree. The first level is a memory table that is protected by wall, like shared buffer, but it is not shared buffer because it is just appended in the LSM tree.
Do you
So
want me
for
to share? Yeah, let me do this. Let me share while you're discussing. I
yeah,
have this graphic for you that you're actually
yeah,
discussing. That's you, right? That's the mem
perfect.
table. Yeah, the
So for the
mutable mem
moment,
table.
what we see is that my 16 megabyte went to the mem table only, and that's sufficient because it is protected by wall. If the node is down, then wall can recreate it. And if you have multiple nodes, it is also replicated in another one.
Mm-hmm. And this is your
So
storage, like this is your SS table, right? This is what happens
yeah,
when this mutable mem table grows to some extent, then it will be
yeah,
converted to immutable table and eventually it will be flushed to disk. So this is different from Postgres, folks.
I
This
will
is the
run
difference.
that multiple times to see when it grows. For the moment, it stays in memory when it's not so big. And then when I insert many times, so I still use the same size of buffer on the Postgres part, on the Postgres backend, because it's just multiple copies that are committed at the end. And you start to see that this memory table increases because each copy happens 16 megabytes of rows. And then there is a limit. There are some thresholds that redefine a percentage of memory that can be used for the mem table. And when the limit is reached, this is where the mem table is flushed to a file. And this
Mm-hmm.
is why I start to see one and then two SSD files there. And this mem table back to the initial size when it is flushed, and then inserting again in it. So after some inserts, you just see that the mem table grows and then it's flushed, and then grows and then it's flushed. And the real size of data finally is the total size of the SSD files. And here is the number of SSD files. So when you continue to insert, so the nice thing is that inserting new rows just happens rows. Doesn't have to go to a buffer, write to it, update it. It's just happening. And then it is flushed, and the files, when there are too many SSD files, then they are compacted into one. Because we have not seen the read for the moment, but at some point you will have to read it. You don't want to read too many files, and this is why they are compacted.
Do you want me to
Okay.
show this diagram for the read path if you want?
Yeah,
Yeah, let me, I have, this is something that I prepared for one of my talks. Yeah, this is the read, right? So like what Frank, you're discussing that how, if let's say you need to, if you have several SS table files, right? You have mutable mem table, you have a mutable mem table, you can get to this read amplification and you don't want to read too many from too many places. And how this happens, eventually we have this compaction process that goes and shrinks all your existing SS table to one. And it also what we discussed in the past, right, during our MVCC session, in this SST table file, we also store different versions of the columns and rows whenever you update your data in YugabyteDB. Back to you, Frank.
yeah. And then while you were showing that, I've also triggered a manual flush and a manual compaction just to show what happens when it is flushed and compacted. At some point, I'm not inserting anymore. Everything was flushed, so no space allocated in mem table and only one file there. The big difference with Postgres or Oracle is that we have two kinds of memory structures, one for the writes, mem table, and one for the reads, as you have seen. The reads have to read from the file, and here it's interesting to have a cache, not to with the only reason of performance. So for the moment, this cache is called block-based table. That's the RocksDB term for this metric. And for the moment, you can see that it is quite small. What I did was just inserting rows. Of course, when you insert in a SQL table, it has to read to be sure that there are no duplicate keys, for example. And when you so it has to read, but not all the rows. Now, if I run a read that reads all the rows, I expect to see this read cache growing. So I will run that with an
So that,
explain
yeah,
to
once
detect it.
again, that read cache that you showed is for the SST files, right, that are on disk.
Yeah.
That read cache, because what you
So
have in mem table is more like shared buffers in Postgres, right? It stores whatever can fit in memory, the latest data, right? It can be dirty. It's usually dirty if you update this stuff. But also
Yeah.
Postgres uses operating system cache whenever it needs to get to the data that is not in the shared buffer, but it's on disk. And in the YugabyteDB
In
cache,
yeah. In Yugabyte, we also use the file system cache, which can be sufficient when we read from SST files, but there are some parts of the SST files that can be managed better in a specific cache. And for example, if I refresh there, I can see that after selecting all my
mhm.
rows, I have 700 megabytes, so about the whole size of the SST files, that is in this block-based table. So we have also a cache. It's just that there are two different structures. This cache there is only for reads. Nothing will be updated in the SST files. The only thing that can happen as write to SST file, it is when it is flushed or compacted. So this cache is very different from the shared buffer. The goal is not to have multiple sessions updating the same blocks. It's just a cache for read. Every write will go as new version to the mem table. And something else, for the moment, you can see that it's all blue, called regular DB. There is a higher level of consistency, of complexity when we use consistent acid properties. If you remember, before this copy, I have set disable transactional rights. When you run, so that's okay, that's faster for bulk load, but when you run SQL transactions, you run full ACID properties. So you use the default where transactional rights are enabled, which means that disable is off. I'm not always a big fan of those parameters with a negative thing in front of it, but yeah, why not? And then if I do the same, loading some rows, something different will happen, because when it is a SQL transaction, we cannot write directly to the regular DB, the one that we have seen in blue there, because we need to write the commit time so that other sessions can see if it is committed change. But you don't know the commit time until the end of the transaction. So for that, in YugabyteDB, what we do is that we write first to an instance DB. You can see instance DB there. The provisional records. It is written to an instance DB with the same structure, a memory table. I just show it in different color there, but it's the same, a memory table. That can be flushed to SST files. And then at commit, this one can be used for reads. And in the background, they will go to the regular DB. So what you see when I'm inserting many rows with the transactional way, you see this instance DB growing and being flushed to SST files, and regular DB also taking them. The big difference is that instance DB holds data only for the ongoing transactions, and usually you don't have a large volume of it. So usually this instance DB stays in mem table without being flushed to a file, or maybe one small file. You see the size of it is really small there.
So the
And if
purpose
I
here is like, yeah, if to compare to Postgres, and Postgres, when you are updating records, you will be generating, let's say, the new versions of the records, and those new versions of the records will be stored in the same heap space of Postgres, where you store the dead records, the old records, and the new ones. And then you have this Postgres vacuum process that needs to start up, and go through that heap space and clean all the unused versions of the rows.
and there are also the B-tree blocks that are
Mhm.
always updated, always modified.
Yeah, in our case, at least, we are already running across several machines, and we are searching for the ways how to optimize our SQL engine and storage layer. That's why this IntenseDB helps us to generate much less garbage in the primary versions of the storage, right? So because then when you run compaction, you basically do this faster. Certainly, when you do the compaction of your regular uh, database files, right, regular SST files, you will find some of the versions of the columns and rows that no longer needed existed. But at least you also probably would kind of, if you were storing everything in the same place, if you did not have the intense DB, then probably the size of those regular system type table files would be much larger, and that could have impacted not only the write path but also the read path of your database.
And also a big advantage is that when you read from regular DB, you know that the transaction is committed. When you don't have that, then you need to do more work to see if it is committed or not. To go to the transaction table, to check the transaction ID and all that. So the big advantage is that in regular DB, we have something that is all committed. In intense DB, you have uncommitted changes, uncommitted ones. So it is smaller, but when you read from it, you need to look at the transaction status. When you read from regular DB, you know that it was committed and you know at which time it was committed. So basically, to recap the main memory structures in YugabyteDB, the work memory of the Postgres backend is nearly the same. We don't need as much of it. For example, when you create an index, you don't need to sort everything. You can just append it on the LSM tree. So you don't need that for create index. But for many things, queries, hash join, you still need the memory in the Postgres backend. And then you have two places where memory can be allocated to get fast writes. That's the mem table that gets all the writes, and the block-based cache for reads, just to keep in an optimized cache the blocks from the SST files. And of course, not all SST files will fit in memory. That's not the goal, but at least the most important part. For example, there are Bloom filters, there is some metadata about the files, and this stays in memory.
Yeah, this is as we highlighted, folks, in the beginning. It's this topic is very broad, but at least our goal was to show you, let's say, how those databases are connected in different. And Frank, I want to quickly go back to that work memory. Like in your Grafana dashboard, you show that you have this work memory of Postgres, and I briefly discussed the work memory of Postgres on my diagram in the past. When I start, like right now, you have just one connection to YugabyteDB, right? And that explains when you have. But what happens if you open multiple connections to YugabyteDB? YugabyteDB will also start multiple backends of Postgres, right? And every backend will have its own work memory.
And they will allocate memory for prepared statement, for execution plans, for work memory. So yeah, they take. One thing, if I can run it very quickly, one thing that is really interesting with Yugabyte LSM trees in general is that when you create an index, for example, let me set the work memory very high so that I can use 500 megabytes. And I create an index on my table that was a few hundred megabytes there. And this in Postgres will use a lot of memory, because a bit tree, to create a bit tree, you need to read all the rows, sort them, use memory for that, or temporary file. The nice thing with the LSM trees is that we create indexes just by inserting into the LSM tree, going to the mem table. So now if I look at the statistics for the index that I'm currently creating, so you can see that I don't use much more on the Postgres backend. I just have one more that is backfilling the index, but not using a lot of memory. But then I have the mem table for the index that is growing. So creating an index is like inserting, because there is not this overhead like in B-trees where you have to go to blocks, split block, and all that. That's one nice thing with LSM trees.
Yeah, and the mem tables, because when we talk about those mem tables, shared buffers in Postgres are just buffers. They're connected to each other, but those buffers are not. It depends. If that's just for the regular data, this is the heap data. It's basically spread somehow, and Postgres needs to scan those buffers. Mem table is a tree. It's like some type of index. It can be red, black tree. I don't know. Like it depends on an implementation, which means that it's already sorted. It's already fast, right? Search through that tree. What I want to conclude, but nevertheless, let's. I want to show this diagram one more time, just to conclude on. Sorry, just to draw this similarity between YugabyteDB and Postgres, because most of the stuff that we showed you today is storage related, and storage wise YugabyteDB is different from Postgres. But this very beginning, when you have clients that are yet to be connected or clients that are connected, this stuff is the same in Postgres and YugabyteDB, and this is what we reused. YugabyteDB reused from the Postgres ecosystem. We reused the query layer, sort of your compute engine, which means that, like, you remember Frank was showing you that walkmem statistics of Grafana. Postgres has the same stuff because we are using the Postgres backend. And whenever, let's say, now imagine that your clients decided to switch to YugabyteDB and they are going to connect to YugabyteDB. In fact, they will be connecting to Postgres Postmaster, and the Postmaster will be opening as many backends of Postgres as necessary. But what's different, if you are running on Postgres, this is your storage, like not a complete picture of the storage, but some of its area. And I demonstrated you today this shared buffers stuff. But in the YugabyteDB case, instead of this storage layer, we are going to have what Frank showed you, LSM trees with mem tables, with SST table files, and also it's going to be distributed, right? It's going to be distributed across several machines. Does it sound good enough, Frank, as a summary, or you want to add anything else?
No, yeah, that's perfect, and it's important to understand how it works when you start to troubleshoot performance. You need to understand which operations are faster, which ones may need to scale, and also memory allocation on the
All
server.
right.
You need memory on the servers for all those structures. Do
All
not
right.
try to always use all memory. You need available memory. If on Linux, if you type top or free, you need to see some available memory because it is needed by any database.
Yeah, you don't want to have a memory out of memory exception in production. But
Exactly.
this is a different topic. And yeah, like Postgres FM podcast by Nikolai and oh, I forgot the name of the second host. It's a wonderful. They discussed a lot on what are the best settings if you're using Postgres. What are the best settings for walkmem, for shared buffers, etc., etc. So, folks, if you are not listening to the Postgres FM podcast, do it. You can watch it on YouTube, or you can just listen it on Spotify or another streaming platform. All right, so like let's quick, folks. We are already beyond the allocated time. It usually happens when we go into those internals, but hopefully you liked it. Just if you have any questions, let's see, like last 5 minutes. We are ready to stay to answer the last questions. I'm checking on LinkedIn. And those of you who didn't make it to this live stream today and are watching us on demand right now, hope you also enjoyed it. And if you have any questions that are not covered, because something might be not clear, something might be a little bit vague or like way too abstract, you can always find me and Frank on our YugabyteDB Slack community, or just find us on Twitter or LinkedIn, like this under our names. You have Frank for sure. And Denis Magda, that's our also Twitter handle. You can find us there and ask us questions.
And we love questions for many reasons. First, to help, but also if there are questions, it also means that we need to produce more content or put something more in documentation to make it more clear. And also there are some questions where we have to dig and investigate and ask to the colleagues in engineering. So it helps also us to learn and at least to explain it better.
And Frank, if you thought that that would be the real end for our live stream, not yet. We've got a question from Yogi. How about temp tables in YugabyteDB? Where are they stored and on Postgres?
So the temp tables, the nice thing with temp tables is that you don't have to distribute them because they are local to your session, and your session backend is only on one node. So they are stored locally. Maybe we will do that differently one day. But for the moment, they are just local to the server.
Yeah, what when it comes to
Under
Postgres,
the PG data path, I think.
yeah, let me try to reproduce this. I've never tried this, but in Postgres, where is it? Where is it? In Postgres, let me find this one. Yeah, it's here. In Postgres, you have this temp buffers area, and this one is private for every backend, meaning that every session that connects to Postgres will have its own temp buffers associated, and this one stores data for those temporary tables. Probably if I will be able to reproduce it within a minute, let's create table sample temper with ID of integer type. Is it called
And
as temporary?
something that I can add also that is very, very important. Yugabyte table are stored differently. Postgres, the temporary tables in Yugabyte uses Postgres. For example, if you create a temporary table and you \d on it, you will see a bit tree, not a LSM tree.
Uh-huh. And I was
Because it doesn't need to be distributed, and then we just reuse the Postgres code. So in the code of Yugabyte, we do things differently if it's a temporary table or if it is a distributed table.
okay, and I just created this temporary table sample temp. It's put into this schema. That's my first other connection. You can see that this table is not visible because this temporary. Let's quickly insert into sample temp some values, right? 1, 2, and 3.
And we can see that how Postgres works with temporary tables. They put a temporary schema. So when you \d, you see a temporary schema.
Cool, cool. So I see it, right? And if I do this explain, analyze, and we do buffers, we want to see the buffers. So this time it's local hit. See? It's local.
Yeah.
It's not shared, which means that it's reading from that private memory, and this one is not visible to the other sessions. And if you do it here, you don't see this table at all. It's just private. So once this session ends, this one will disappear. It will be removed from Postgres. So let me reconnect. Password. No, it's gone. So the process is gone, and all the memory that is associated with that process is gone as well. I guess this answers. Let me see what else. Any follow-up questions from Yogi?
And temporary tables in Yugabyte, you can also use the buffers because you will see the number of buffers from it.
Yep, and we've
Not
got
the shared buffers, but buffers. Yeah.
So let me from Faith, Faith. Sorry, sorry, my friend, if I mispronounce your name. So first, a great session, guys. Thanks. I'm curious to learn more. Looking forward to seeing more of these internal sessions. Yeah, that's also our plan. We want to do more of them. So, and another question, follow-up question from Faith was, I'm sharing it from LinkedIn. It was either any storage internal session recorded already. So I think that we should have some stuff available as part of our YugabyteDB Friday Tech Talks, right? If I let me do this, I will share with you a link, and I will share my screen with the others, so that you folks can find it. It's under the community YugabyteDB Friday Tech Talks.
Yeah.
So it's a huge collection. I think we already have over 100 episodes.
100 sessions only about internals, because those sessions are made by the engineers who are building the database.
Yeah, we are not building the database. We are helping to adapt it. We are helping to use it, and
We are just
using
users.
application. Yeah, we application. Yeah, we use it. We take it.
We are
use
users who like to understand how it works.
All right, I shared it with you folks. Anything else? The final restart, and then we are closing this live stream, and then we will see you folks next time. So that's it. No more questions. Thanks everyone who attended, and enjoy this stream for those of you who will be watching it on demand. And we will see you in a couple of weeks. Right? Bye bye now.
Thank you. Bye.